Furnace Improvements has many years of experience helping end users and owners to improve the efficiency, capacity and optimizing their fired heaters, boilers and waste heat recovery units. FIS also helps to reduce NOx emissions. In this video we will cover fired heater optimization to save money. Tuning a heater will increase your efficiency, reduce your fuel consumption, increase your run length and decrease your maintenance cost.
If we look at three major industries, we will find that all the three are energy intensive. Typical energy consumption is approximately 0.40 million British thermal unit per barrel of crude oil processed. Looking in the ethylene industry, the average energy consumption will be 22 MMBtu per ton. In the ammonia and methanol industry, the consumption will be 28.5 MMBtu per ton approximately. These industries present huge optimization opportunities.
In a typical refinery, 2/3 of the operating cost is fuel cost. For example, if we have a regular size refinery which will be processing 100,000 barrels per day, with a typical energy pricing of $6 per million British thermal unit and requiring 0.40 MMBtu per barrel of crude, the energy bill will be $87.6 million per year. Increasing the total fuel efficiency by only 1% can translate in savings almost $1 million per year. It is our experience that 1 to 1.5% reduction in fuel consumption can be achieved by good housekeeping. 2 to 4% improvement in efficiency can be obtained with minimal investment in better controls. These schemes can pay out in less than a year.
Fired heaters are an essential component of most process plants. They are primarily used to heat all types of hydrocarbons and also hot oils, steam or air. Each refinery has between 20 and 50 fired heaters. Typically, most fired heater operations can be optimized to save money by reducing energy use, having a longer run length, and extending the equipment's life with a minimal maintenance. In a fired heater, heat liberated by the combustion of fuels is transferred to fluids contained in coils. A fired heater consists of three major components: heating coil, enclosure and combustion equipment. It is required to have some instrumentation to get an idea of what has happened inside the fired heater and to maintain desired operating conditions. Two major controls are fuel firing control and the feed flow control.
Combustion is an exothermic reaction resulting from a rapid combination of oxygen with fuel. Since perfect mixing of fuel and air is not possible, excess air is needed to ensure complete fuel combustion. For every part of oxygen, 4 parts of nitrogen enter the combustion process and leave without reacting. The N2 absorbs some of the heat and carry it to the stack. It is necessary to minimize excess air to avoid excessive heat loss. But it is undesirable to operate with less than stoichiometric combustion air, as it will lead heat loss and release of carbon monoxide and hydrogen. These last two are combustibles and could burn in the convection section, causing damage to the tubes and fins. Your aim should be complete combustion. And then, excess air reduction. Draft is the negative pressure that is created inside the heater as a result of the differential temperature from the hot flue gases inside the heater and the cold ambient air. Combustion air is drawn into the burners and hot gas flows out the stack due to this pressure differential. While passing through the convection section and stack, flue gases encounters friction resistance. Sufficient stack height is provided to overcome these losses and ensure that pressure is always negative inside the firebox. The heaters can be classified by their draft. 4 types of draft exist. Natural draft depend on their stack. The taller the stack, the more draft available. Forced draft, in this type of system, air is supplied by centrifugal fan commonly known as a forced draft FD fan. Induced draft, when the stack's height is inadequate to meet the draft requirements, an induced draft ID fan can be used to draw flue gases out of the heater. Balanced draft, when both FD and ID fans are used with the heater, it is known as a balanced draft system. Most air preheating installations are balanced draft and in general around 10% of the heaters are BD.
This image shows a heater's draft profile. The heater's arch or convection section inlet is the highest pressure point and is used as a control point. A typical value of 0.1 inches water column is maintained at the arch. A high draft leads to more combustion air drawn into the firebox. Conversely, insufficient draft may lead to positive pressure inside the firebox, leading to flue gas leakage from any openings. Both scenarios lead to heat loss and decrease of the efficiency.
A good operating practice is to look at the heater once per shift to confirm that the firebox is clear, there is no smoky appearance, burner flames are steady and well formed. It is highly recommended to check burners regularly for any signs of blockage or unusual flame conditions. If the burner flames are long and lazy, it is a sign of poor mixing. Increasing the airflow to the burner can reduce flame length. It is also necessary to control the air intake. Excess oxygen control is normally done through burner register in all natural draft heaters. In balanced draft heaters, FD fan dampers control the air supply.
Since pressure inside the heater is negative, all air leakage must be eliminated. To minimize the air leakage into the heater, all peepholes must be kept closed. The header box doors must be tightened. Recently we saw an installation where there was a gap of half to 1 inch on the header box bottom. This gap allows air to get into the heater. You also should ensure there is minimal air leakage from the tube guide penetrations in the floor. The unused burners can also filtrate air into the heater. It is important to review this opening to minimize the air filtration. The problem with this air is that it doesn't mix with fuel gas and doesn't take part in the combustion reaction.
Recommended excess air level in the flue gas for gas firing is 2% to 3% oxygen. For oil firing it is 4% to 5% oxygen. The performance of each fired heater can vary easily, and that is mainly because of the manual control and adjustments that the operators have to make every day to the heater. The number of operators are less, and most of the times they don't have the required experience to deal with the problems that a fired heater can have. As we saw in this presentation, optimizing fired heater performance is possible by making minor modifications and practicing good housekeeping.
In the following slides we will demonstrate with examples how to increase the efficiency of a fired heater with minor modifications. A few months ago, my company had the opportunity to perform a tuning job for a refinery. The heater was a depentonizer reboiler with horizontal tube box and 15 up-fired burners. The heater has 2 offtake ducts provided with manual dampers. Both of the ducts were connected to a large common stack. The absorbed heat duty of this fired heater is about 87 mmBtu per hour.
To optimize the heater, our team checked 3 points: the draft, the excess air and the burners. For the draft they made the adjustments using the offtake dampers. To get the minimum excess air, FIS team adjust the burner register, and they also light up all the burners, and check the flame in the firebox to discharge any problem in the radiant section. The results are plotted in the following graphs.
Reducing the draft reduces the air leakage in the system. We want to eliminate any leaks from header boxes, peepholes opening and shutdown burners. Most of the burners, even in shutdown position, leak 3 to 5% air. In this particular case, FIS team decreased the draft from 15 to 7 mm water column.
Draft reduction decreased the air across the burners and minimized the quantity of combustion air going into the burners. We were able to reduce it from 4 to 5% to 2% air level without any monoxide carbon formation.
The depentonizer reboiler has 2 off-taken ducts which are connected to a common stack. These 2 readings correspond to the flue gas temperature at the beginning of the 2 off-taken ducts. You can clearly see the decreased on both readings. It decreased from 335 degrees to 300 degrees Celsius. The reduction of approximately 35 degrees in flue gas temperature is due to the decrease in the quantity of the production of flue gas, which was reduced when the excess oxygen decreased from 4 to 2%.
These adjustments had a direct impact in the performance of the fired heater and in the efficiency. In this case, the efficiency went up by 3%. In terms of savings units, this means the following. This fired heater has a firing rate of about 100 MMBTU per hour. The price of each MMBTU per hour is around $6. At the end of the year, the refinery will be saving more than $150,000 just for doing the adjustments already mentioned.
Another example is the tuning job that furnace improvements made on a crude heater. This was a natural draft crude heater with horizontal tube and 12 up-fired burners.
The graph presents two sets of data for the fuel gas flow and fuel gas pressure in the heater. The one on the left represents the heater normal operation before any tuning work is done. The data on the right shows a decrease in the fuel flow and fuel gas pressure due to the tuning work made to the heater. With the heater capacity remaining constant, a reduction in the fuel gas flow represents an important energy and money saving in the heater operation.
Nowadays, a very common practice of heater operation is to have a number of burners working, while keeping some burners off. There is no such thing like keeping a spare burner off. The heater is designed to run with all the burners. This graph shows the tube skin temperatures before and after lighting up all the burners. A more uniform heat transfer occurs in the firebox with all the burner lighten up, which translate in a better performance of the equipment. The crude heater easily became more efficiently just by doing minor adjustments.
One of the major observations that we commonly find in the refineries are furnace working off design conditions, poor quality of dampers, lower number of operators, operator without sufficient training. To ensure the most efficient performance on your fired heater, we recommend the following FH support. Software Heater Performance Index. Hardware reliable dampers, control systems for draft and burners.
The HPI software can be used for all fired heaters to monitor the performance 24 hours per day. It is an online tool for continuous monitoring of heaters. With the use of HPI software, the current performance of the heater is thoroughly analyzed by taking live data from the DCS and performs calculations. HPI is custom built. HPI will check high tube metal temperatures, coking inside the tubes, excess fuel gas pressure, draft, stack temperature, many others parameters.
HPI helps increase the run length of heaters and take corrective action. Any significant deviations of the key process parameters from the desired values are highlighted and can be corrected. It will generate various messages to provide guidelines for the operator and safe and efficient operation. HPI will ensure your heater always performs the best possible.
A damper is an important component that every heater requires, but most important is to have a reliable damper. There are different types of dampers and each one has their own characteristics. In this slide we put side by side the performance of the opposite blade and the parallel blade damper. The opposite blade damper gives to the operator more control during the openings than the parallel damper.
The scheme shows two independent control systems. The first one is the oxygen control system that controls the burner's registers. It works limiting the amount of fuel burning in the burners, and the fuel quantity will be determined by the flue gas temperature at the arch. Each burner will have a pneumatic operator at the burner register. The second control system is the draft control, which manages the stack damper. The stack damper will be adjusted depending on the amount of draft at the arch. With these two control systems, you will ensure an optimum performance 24/7 at all loads, especially in turn-downs. Our company, FIS, is planning to implement these control systems in the heater we have shown at Case 1.
We appreciated your time for listening this presentation. We hope this presentation can help you improve the performance of your fired heater. Any comments or questions welcome. Please contact us by email or by phone.